Reading assignment 4, section 1.5, problem 79. I'm going to do just parts E and F from this question. The other ones are fairly similar. The question asks is about inverse force fields. It asks you to consider the radial field like this, where F equals to R over magnitude of R to the power of P. R is a vector x, y, z, and P is some integer, I think. Yes, actually it doesn't say that it's integer. It's some number greater than 1, and they say the inverse square law corresponds to P equals 3. Now, why do they say this? That's because imagine P, so this R over R to the power of P can be rewritten like this. You can single out R divided by magnitude of R, and then what's left is R to the power of P minus 1. Now, this part is a unit vector that tells you the direction of F. And this part is the magnitude of F. Now, the unit vector in this case is pointing away from the origin because x, y, z is just the position vector, and so imagine this is the origin, and then we're at some location x, y, z. Then r points away from the origin. It has this length, so it's going to look something like this. Then you're scaling it, so this would be unit vector in this direction. So I guess this is R, R divided by magnitude of R is a unit vector in this direction, and then it's scaled by this. Okay, now what happens when P equals 3? When P equals 3, we get magnitude of F equals to 1 over magnitude of R to the power of 2. So the force, this field, decays at a rate of 1 divided by magnitude of R to the power of 2. That's why it's called the inverse square law. Okay, so then we have the line C. You're given the line C, that is a line from point 111 to AAA, where A is some number greater than 1. Okay, let's sketch that. So we have the origin, we have a point 111, and we have another point that lies on this same line, A, and yes, so it's this line. The line is parameterized like this. So R of t equals to t for t going from 1 to a. So the parameterization of this line is given by t for t between 1 and a. Now, the reason it makes sense is because, okay, so when t equals to 1, we start off at a point 111, right? R equals 111. Then t increases, and then the direction of the traversal on this line is going to go from this initial point to the final point. So the parameterization implicitly tells you what the direction of traversal is. And then they ask, find the work done in moving an object along C for any p greater than 1. So in this case, along C, they mean in the direction of increasing t. Now to find the work, you would use the definition of the work integral. This is something you should have seen in the textbook, I think. Now let me just explain what this integral means. So you can think of it this way. Let's say you have, let's take an example of p equals 3. And this would be gravity, for example. So you would have a massive object at the origin, and then you are somewhere here, and there is a force pulling you towards this massive object, right? But you, in order to move away from this object along C, you need to apply the force that goes outwards, right? So the force you need to apply is going exactly the way this radial field goes. So this is what meant by F. It's not, they don't, so I don't want you to be confused when they say field. It's, you know how field points towards the massive object, gravitational field, but that's not what they mean by force field here. They mean the force you're applying. Okay, so in part F, they are asking if A approaches infinity, so if this point moves infinitely far away, for what values of P is the work finite? So let's do it. First, let's find the work. They already parameterized the line for you. From this, you can get differential length element, which is r prime dt. R prime equals to 1, 1, 1. All I did is I took this and I differentiated with respect to t. So the differential length element is 1, 1, 1 dt. Now, when you're integrating, you would be integrating over the parameterization variable. This r prime dt is the length element with direction associated with it. The field needs to be evaluated at the line. So field on C, that's why I plugged in x of t, y of t, and z of t. The bounds on t would be from 1 to a. Here I plugged in what f is. It's x, y, z divided by r to the power of p. On the next line, I wrote, I plugged in x of t, y of t, and z of t. Another thing I did is I figured out what magnitude of r is, or magnitude of r to the power of p. So let's do it. We know that magnitude of r is square root of t squared plus t squared plus t squared. Or let me do it in 2 steps. It's x squared plus y squared plus z squared. All to the power of p. I can rewrite it as x squared plus y squared plus z squared to the power of p over 2, because it's a square root. And I can also plug in t for x, y, and z that I get from the parameterization, right? Because parameterization is x, y, and z equals to t, t, and t. So then I get 3 to the power of p over 2, and I get t squared to the power of p over 2. But this square and this square cancel, so we get 3 to the power of p over 2 and t to the power of p. That's what I wrote here, 3 to the p over 2, t to the p. On the next line, I expanded out this dot product. And I got 3t. And then if you divide it by 3 to the power of p over 2 and t to the power of p, what I wrote here is 3
to the power of 1 minus p over 2. This is because we have 3 in the numerator, and we have 3 in the denominator to the power of p minus p over 2. And then t to the power of 1 minus p is here. On the next step, I integrated. The way so I wrote 3 to the power of 1 minus 1 to the power of 1 minus p over 2, and then t to the power of 2 minus p divided by 2 minus p. But we need to be careful because this only works when 2 minus p is not 0. So this is the case p not equal to 2. When p equals 2, we need to integrate it separately. So let me do that. If p equals 2, we have 3 to the power of 1 minus 2 over 2, t to the power of 1 minus 2, which is 3 to the 0, which is just 1, and t to the negative 1. And when you integrate 1 over t, you get ln of absolute value of t. Now I evaluated this at endpoints a and 1, and I got this constant. Then 2 minus p stays the same, and now I plugged in a. I got a to the power of 2 minus p minus 1. Here I got ln of a minus ln of 1, but ln of 1 is 0, so we only have ln of a. So we are done with finding work for arbitrary p. Now let's figure out when it's infinite. To do this, I considered 3 separate cases. One is when p equals 2, and one is when p is less than 2, and one is when p is greater than 2. You'll see why I chose these in a second. For p less than 2, we have this constant. We have, I just simply copied this formula over. And when p is less than 2, this is some positive number. So is this. And this is also positive because 3 to the power of anything is positive, is a positive constant. And when a approaches infinity, we have a to some, so we have greater and greater number to the power, to some positive power, minus 1. This still approaches infinity. This entire numerator approaches infinity. And when you divide it by some positive number, by constant positive number, this is still approaching infinity. And then multiplying the whole thing by this positive constant still keeps it approaching infinity. So for p less than 2, work approaches infinity. When p equals 2, we have w equals ln of a, and this still approaches infinity as a approaches infinity. You can see this from the graph of w versus a. I'm only going to sketch it from 1 onwards because a was given as greater than 1. And ln keeps increasing. Increases very slowly, but it increases to infinity. Actually, I didn't draw it quite right. It's more like this. So it is very slow increase, but it will eventually go to infinity. When p is greater than 2, well, it's still the same formula, but now this guy is a negative number. So I didn't want to deal with negatives. So instead, whenever I saw 2 minus p, I swapped the 2 and put a negative. For example, on the denominator, we see 2 minus p, so I swapped the two things, and because of this, I also swapped these two things. That's the same thing as multiplying by a negative number. So now I have 1 minus a to the power of 2 minus p. But a to the power of 2 minus p equals to 1 over a to p minus 2. That's why I wrote this over here. Now we have a, you see now p minus 2 is a positive number. So we have this is positive. This power is positive. So we have 1 over a to a positive power. Now, a number a to p minus 2 approaches infinity. So this fraction is going to approach 0. And when we have 1 minus 0 over something multiplied by some number, we still just get a finite number. We get 1 over p minus 2 times this. So this is finite. So the only case where work is finite is when p is greater than 2. One example of p greater than 2 would be gravity. That's where p equals 3. So if you have a massive object and you're located at some point, well, we only did it for a specific case 111, and we didn't really take any correct forces into account. You see, gravity is not equal to this. Gravity is equal to some constant times this. But just conceptually, if we have an inverse square law, so p equals 3, we know that we need finite amount of energy to go infinitely far away from the massive object. So this means that if you have, let's say, if you have some amount of fuel, then you should be able to move away from the object. And it's not an infinite amount of fuel. You know that there is enough fuel. There is the amount that's enough fuel to get away from the massive object.